Okay, let's get a quick little sound check here. There goes the echo. Okay, so sound is working. We are back on and live. So welcome back to another installment of Atari 5200 programming for... I'm not going to say for dummies, for anyone who's interested. Let's put it that way. So last week, unfortunately, I was running into some technical difficulties and I was not able to do the stream. I have mostly resolved those now. So should be okay, at least for today. Things are good enough. There's still some problems, but they're not super bad. So what do we have here? Well, let's see if we can figure out where we left off 2 weeks ago. So 2 weeks ago, we got this little toy project to the point where we have a cool background. We got a cool little ship thing here on the bottom that we can move left and right, and it hits the edges of the screen and stops, and it can shoot. Look at that. We can shoot missiles at the top, up to the top of the screen, where they're reset and then come back to the bottom. How cool is that? And toward the end of the last session, we also put in some code to prevent the attract mode from kicking in, which is something that a lot of people forget about until they see it happen and they realize, oh yeah, I forgot about that. So that kind of sums up everything we got done last time. Now, I want to start off today by correcting a couple of mistakes. I was going over some stuff from the prior video, and I saw a couple things I wanted to fix. So first of all, the first problem is with the display list here. In particular, the very last line of it. So this is supposed to be the memory location that we're going to pull the data from for the line on the bottom, the text line on the bottom. I put the address in here incorrectly. Should be 2820. The funny thing was that during the video I actually said that, but I didn't type it. So there it is. We fixed that. So now the bottom text line will work correctly once we get around to putting something there. Now the other thing I noticed was that for some reason I never used the bottom row of the sprite. I think I padded it with zeros at the top and the bottom to aid in vertical motion. And I think I looked at this bottom one and said, oh yeah, that's my bottom zero. I didn't realize I'd space them out like this. So I'm going to go ahead and put something down here. I'm going to put another row of sprite data there. There we go. That'll be cool. All right. So let's go ahead and look at it now with the new sprite data, just because. It's barely a change, but I want to do it anyway. Okay, look at that. Looks even more like a turtle now. Great. I'm calling this the pink space turtle. That's going to be my name for it. Okay, so we're all coffeeed up on this Friday night. Last weekend was the Portland Retro Gaming Expo. So last weekend that would have been October the 15th of 2022, which was a fun show. I went down there, met a lot of people, talked to a lot of people. Talked to a lot of people about Robin Banks and the other games I've done. It was a really cool show to go to. And I go to it almost every year. Already kind of looking forward to next year. But let's talk about what we plan on getting done today. So my biggest plan that I had last week, well, 2 weeks ago for this stream that was supposed to be last week, was that I wanted to start messing around with the wonderful world of display list interrupts. And specifically, what I was looking to fix was the two text rows. So at the very top of the screen, we have a row of text. Right now, it just looks like a gray rectangle. And we actually have another one at the bottom of the screen, but you can't really pick it out because it blends in with the moon surface. Now, the colors are screwed up on those two text rows because the way color works in that text mode is a bit different from the way it works in the other graphics modes. Which means we're going to have to play some color games and actually change the colors between modes. And the way you do that is with something called a display list interrupt. Now, of all the things you can do with an Atari 5200, in my opinion, display list interrupts are really kind of the most difficult thing. They're very finicky, they're very sensitive, and they can be a real pain to get right. But most of the advanced graphical techniques on the 5200 rely on display list interrupts. So you need to learn how to do them at some point if you're going to do anything of note. So what we're going to do here is fix these colors. That's the first thing we're going to do. So let's talk a little bit about displayless interrupts and what they are. Well, given that they're called a displayless interrupt, you're probably thinking already, well, they have something to do with the display list. And you would be correct about that. So here we are down here with our display list, which I will quickly review again, just in case you've forgotten how this works. So the display list describes to the Antic chip how to draw the play field from the top of the screen down to the bottom of the screen. So each of these bytes means something to the Antic chip. And for every frame it's displayed on the TV, it goes to the top of the display list, runs through all these bytes, and does whatever they tell the chip to do. And then it goes back to the top, waits for the next screen draw, and does it again, over and over and over again. So these first 3 bytes here are typical for a display list. At the top of an NTSC television, there's an area called the overscan. And the overscan is not guaranteed to be visible on every television. In fact, most televisions, a good chunk of it is not. The general rule is you skip 24 scan lines, or the horizontal lines that are actually drawn by the TV. You skip 24 scan lines and now you're in the visible area. That's the general rule. So this instruction here, this Antic instruction, I'm going to go over the Antic instructions in a little more detail now because we're starting to get into the good stuff. So this is how you read an Antic instruction. First, you look at the least significant nibble. This tells you what type of instruction you're looking at. So if the least significant nibble is a 0, it means that this is a scan line skip instruction. And the most significant nibble is the number of scan lines to skip minus 1. So we want to skip 24 scan lines at the beginning of the screen. So we have here is 0, means skip scan lines, and 7 is the number of scan lines to skip minus 1. So it means skip 8 scan lines. So 3 of these instructions in a row skip 8, 16, 24 scan lines, which gets us out of the overscan area into the visible area. So what's up with this minus 1 thing, you might be asking? Well, for one thing, it wouldn't make any sense to skip 0 scan lines. So this allows 0 to actually mean something. It would mean to skip 1 scan line. But the more important reason is that if you set the highest bit of this Antic instruction, it requests a display list interrupt, which we'll talk about in very shortly. But that uppermost bit is the interrupt bit. So by making this minus 1, it leaves that uppermost bit free, which means you can request a display list interrupt during one of these scan line skip instructions, which I did for the first time in Robin Banks. I didn't even know you could do that, but that's actually very useful in some situations. So moving on, we get to our first real thing. Again, always look at the right nibble first. So if the right nibble is 2 through F, this is a mode line. A mode line is a line of a particular graphics mode. In this case, this is a mode line of mode 2. Mode 2 is 40-column text. Now, each mode line occupies a certain number of scan lines, and you can find documentation on this to know exactly what it is. I happen to know that every line of mode 2 occupies 8 scan lines. So this gray rectangle at the top of the screen, that is our line of mode 2 right there. That is 8 scan lines high. So this instruction for mode 2 takes up that much vertical space. That's one mode line. I'm trying to use my terms very carefully here. That is one mode line of mode 2, which is made up of 8 scan lines. Now, when an Antic instruction, boy, that is tough to say. When an Antic instruction is a mode line like this one, the most significant nibble, the 4 bits here, are special flags that control certain behaviors on that mode line. Now, I've already talked about the uppermost bit nibble. The uppermost bit. That requests a display list interrupt, and it is true for these instructions just as it's true for the skip instruction. But the next bit down, which is 4 in this case, This triggers something called a load memory scan. When this bit is set, it tells Antic that the next 2 bytes that follow are the memory address that Antic is to start reading the graphics data from. And this is in little endian order, so the least significant bit comes first. And here we have 0020. So this means that Antic is going to start reading graphics data from address 2000 hex. So now each mode line is going to read a certain number of bytes. It depends on the mode line. Every mode line of mode 2 reads 40 bytes. So the 40 bytes that are found at address 2000 hex are going to be displayed in that gray box as character codes, as text. Right now there's nothing there. It's all zeros, and 0 is just space. So we got nothing there. But if we were to stick the data there, it would show the letters there. Now, our next instruction here is mode E. Mode E is 160 pixel wide, 4-color bitmap mode. This is the mode we use for the background here with the planet and the moon and the stars and all that. This is all mode E. And here's that 4 again. So we're going to move Antic's video pointer. We're going to get the data from somewhere else now. In this case, we're getting it from background, which is in another file. This is the big bitmap graphics data is sitting in there. So the way mode E is interpreted is it's 2 bits per pixel. So every byte it reads has pixel data for 4 pixels. Every 2 bits is a pixel. And there are 4 colors. You have the background color, which is 0, and then playfield 0, 1, and 2, which correspond to 1, 2, and 3 in 2-bit numbers. So that's how it displays those graphics. And then we have a whole bunch more lines of mode E. Now here, the uppermost nibble is a 0, which means none of the special bits are set. So this just displays another line of mode E, and it keeps flowing through that address. Just keeps going and going and going. Now, down here, we set a new address. And this is because of a weird little quirk about Antic. And I actually demonstrated this on the last stream. For whatever reason, and I did read the reason one time, but I've forgotten it. Antic's internal pointer that it uses to refer to where the graphics memory is cannot cross a 4K boundary. So here, the graphics were crossing a 4K boundary. And what happens when it crosses a 4K boundary is it just loops back to the beginning. So it starts repeating that 4K block again. So I had to reset the pointer here to hop over that 4K boundary so we could continue displaying the rest of the image. And then we keep displaying a whole bunch more mode E. And then at the very bottom, here's another mode 2 with another 4. So we're moving the pointer again. This time we're going to 2820, which is little endian again. So it's address 2028, which is 40 bytes after this upper row, which was at 2000, or this row here, which is at 2000. So we have 4 memory areas we're displaying. There's the top text line, most of the image, the rest of the image, and then the bottom text line. Now this bottom instruction here has a 1. If the right nibble, the low nibble, is a 1, it means that this is a jump instruction. So this instruction is going to go somewhere. Now where it goes is determined by this nibble. The 4 here means wait for vertical blank and then jump to whatever's in the 2 bytes that follow. So the 2 bytes that follow are display list, which is the very beginning of the list. So this resets it back up to the top. Now there is another jump instruction. I can't remember the code for it. It's, the rightmost nibble's 1. I don't remember what the left nibble is. That just jumps immediately to any arbitrary location and continues displaying from there. I used that for the first time in Robin Banks, where I had a situation where I had a display list that was in 2 pieces, and one piece was unchanging and just sat in ROM. And the second piece I had to change, and that one was in RAM. So it would play through the unchanging part and then jump to the part that had to change in RAM and finish the screen, which is really cool. I'd never used that instruction until Robin Banks. But that's that. So that's an overview of what this display list looks like. Now, one thing I will throw out is these control bits. We've talked about 2 of the control bits. We talked about 4, which changes the address you're reading from. We talked about 8, the highest bit, which requests a display list interrupt, which I'm about to cover. What about the other 2 bits? What do they do? So the other 2 bits are used to control scrolling. There's a horizontal scroll bit and a vertical scroll bit, and I can never remember which one is which, but that's what those 2 bits are. Now, scrolling is kind of an advanced topic. I don't know if we're going to talk about that. If we do, it's not going to be for quite some time. But that's what those 2 bits are. So there are 4 control bits: horizontal scroll, vertical scroll, load memory scan, and request display list interrupt. So with that, we can now talk about display list interrupts. So how do these work? So if you change this upper nibble to include the highest bit set to 1, then you'll get a display list interrupt from Antic. And I believe the interrupt comes after the first scan line of that mode. So mode E is a 1 scan line mode. So in the case of mode E, a mode line is a scan line. So it's 1 to 1 all the way down the screen. So if I was to set 8 here, I would get an interrupt after the mode line was done, because there's only 1 scan line. But if I were to do it up here on the text bit, I'd get it after the first line of the mode. I'm pretty sure. Well, we're about to find out. So what happens in a display list interrupt is that Antic gives control back to your program, and it goes to a specific interrupt handler that you set up. And this gives you a very brief moment of time where you can change certain settings about the way the screen is being drawn. Now, I would say the 2 most common uses for this are to change colors mid-screen, which is what we're going to be doing, or to change the horizontal position of sprites mid-screen. This is known as sprite multiplexing. And a lot of games make use of this. In fact, most of my games make use of this. And we are going to do a little bit of this. We're not going to get crazy with it, but I do want to do it once, just to show it. So we will do a little bit of sprite multiplexing. Now, there's some other things you can do here, like plenty of other things. Like you can change priorities, the priority levels for the layering mid-screen. Or one interesting thing you can do, and I did this in Magical Fairy Force. I haven't talked about hardware collision yet, but in the Magical Fairy Force screen, about halfway through the screen, there's an interrupt that records all the collision values for the top half of the screen, stashes them somewhere, resets the collision detection so that the bottom half of the screen can get its collision detection, because you have a player in each half of the screen. So I had to split those so that I could tell who was getting hit from the collision registers, and I used a display list interrupt to do that. All right, but enough talking about it. Let's go ahead and actually write one of these display list interrupts. So, actually, hold on, let me bring that back up. So here's the plan. Here's what we're going to do. The first thing we're going to do is we're going to change the colors as they stand right now. Because right now, the colors are wrong for the very first mode line we display, which is this mode 2 line. These colors are wrong for that mode. So we're going to change the colors to be right for that mode. And then we're going to have a display list interrupt in that mode line that's going to change the colors to what we need for the main screen, for all these E's. And then the very last E, probably, depends, we're going to have another interrupt. And on the last E, we're going to change those colors back to what we need for the bottom line. So that's the plan. We're going to have 2 interrupts here. But the first step is to get the colors what they need to be for that top text line. And I also want to put some text in those lines so we have something to see, so we know if we're getting it right. So we're going to do all those things. So let's start by doing that. So I think the first thing we'll do is we'll pop some text into those areas so that we can actually see that we're doing something right here. So, we'll just throw it right here, right before the game loop. I'm going to do is I'm going to put the numbers 1, 2, and 3. So the character codes for the numbers are 1 followed by the number. So 1, 1, this is the character code for the number 1. So I'm going to take that, I'm going to store it at address 2000 hex. This is the first visible character in that top text row. And I'm also going to write it to address 2028. This is the first visible character in the bottom text row. Then we'll increment X. So now we're on 2. We'll put that in 2001 and 2029. Increment X again and store it to 2002 and 202A. So now we should see, well, we might not see it, depends on the colors, but we might see the numbers 1, 2, and 3 in those two text rows. Okay, is there something there? Yeah, it's there. It's very hard to see, for me anyway, but it is there. Okay, so that was step 1. Step 2 is to fix the colors for the text modes. Now, the way color works in the text modes is a little bit strange. So here we go. Oh, we're also going to talk about the shadow registers here in a bit, but we'll get to that. So in the text modes, color 2 is like the background, I think. All right, I'm going to comment this value out because we're going to want it for the interrupt. So I'm going to try putting 0 in color 2, and we're going to put 0E in color 1. And if this does what I think it does, I'll go back and explain why it's doing what it's doing. Because this mode just has really weird color requirements. There we go. Okay. Oh, wait. What's going on at the bottom? All right. I'm not sure why we're not seeing the 1 down there. Let's go figure that out. It'd be because I typoed it. Okay, so there we go. There's our two text zones. So let's talk again about what we're going to do here. So now the colors are correct for that top row. That's great. We got it. So what we need to do now is after that top row, that text row has been displayed, we need to change those two colors I changed back to what we had them before so that the bitmap, the background, can display properly. And we need to use an interrupt for that. So let's go ahead and set that up. So I'm going to do a little split here, and we're going to head down here. All right. So where are we going to put this thing? Now, I like to have displayless interrupts at a known address. So I can look at it and say, I know exactly where this is. So let's see, this is at A00. Where did we put that? Okay, the background's at 8000, so I'm going to put this at 7000. So I'm going to put the displayless interrupts and start them at 7000 hex. Okay, so this is the first interrupt. I'm going to put a comment here. Change from text colors to background colors. All right. So here's what we need to do. We need to take this old color here, C6, and put it into color 1. But not this color 1. I'll explain that in a bit. Then we need to take this value here, 04, and put that into this color 2. Not that color 2, into color 2. Playfield 1. Playfield 1, playfield 2. We need to change the colors. So here's what this interrupt's going to look like. First thing we're going to do is push the contents of the accumulator onto the stack. Then we're going to transfer Y to the accumulator and push that onto the stack. Then we're going to load into the accumulator the first value we need to write, which is C6. And then we're going to load into Y the second value we need to write, which is 04. Now, I'm going to do this. This is going to be wrong, and I'll talk about it once you see why it's wrong. I'm going to write here to wsync, and then we're going to write to call pf1 pf2. Then we're going to pull something off the stack, transfer it to Y, pull another thing off the stack, and then return from interrupt. Now note, yeah, we'll talk about that in a bit. Okay. First of all, let's see what this does. But in order for this to execute, we need to put it in the right place. And just like all of our other stuff, there's a vector for this. It is called VDSLST, and we probably didn't even set it. Yeah, I never even set it because we never enabled the interrupts. So we never set this before. So we'll go ahead and set it now. We'll put it here with the other vectors. So we're going to, now we put this interrupt handler at address hex 7000. So we're going to load 0, store that at VDS list, and then 70, store that at VDS list plus 1. Okay, so when a display list interrupt happens, VDS list here, this is the address that the antic goes to. It says go here. So it's going to go here and execute this. But we need to actually request the display list interrupt. So we want this to happen after this first text row, because that's when we need to change the colors for the background. So the moment we have the 4-bit set, because that's what loads memory scans, we need to set the high bit as well, the 8-bit. And 8 plus 4 is C. So we turn both those bits on. We have the 4, so it does a load memory scan, and the 8, so we get a display list interrupt. So let's go ahead and run this and see what happens. It's going to be wrong. I can tell you that already, but let's look at it anyway. Wait a minute. It's right. Interesting. Okay, so I was wrong about something. I always forget where the display list interrupt actually happens on a multi-scan line mode line. I thought it was after the first mode line, but it must not be, because if it were, this would be wrong. It must be after the last scan line. But look at that. We got our colors straightened out. Now, there are some points I want to illustrate here. First of all, I want to get rid of these commented outlines here. Okay. Now, there are a couple of interesting things here. So, let's look at the interrupt code itself and see what's going on here. All right, so first of all, you see all this stack stuff I'm doing. So the thing about interrupts is that an interrupt can happen at any time. And when an interrupt happens, the code, the normal execution of code just stops. And the chip goes to the interrupt handler. So you have no idea what the state of the chip was when you got here. And that means that you can't mess up the registers. Because when you go back to the code you came from, you need to be able to pick up from wherever you left off. So it's very important that you preserve the registers that you're going to use. Now, the last interrupt we dealt with was the vertical blank interrupt. But this is a deferred vertical blank interrupt. The actual interrupt, where all this starts, is in the BIOS. And the BIOS saves all the registers. So by the time we get to this interrupt, the registers have already been saved. And this interrupt end routine that I jumped to here is in the BIOS. And this code here restores the registers and then ends the interrupt. So here, this is all being taken care of for us. No problem. But displayless interrupts are a little bit different, because displayless interrupts, every cycle counts here, because you're changing things mid-scan line. Like, you're changing things while the TV is actually drawing the image. So there's no, you can't fool around. You need to be moving on, on top of stuff. So there's no pre-interrupt handler that's going to set up stuff for you and then jump to you, because that just wastes too much time. So in these displayless interrupts, you are responsible for saving and restoring the register state so that you don't screw up wherever this came from. So the first register you will use should be the accumulator every time. because you can immediately push the accumulator onto the stack so that you can get it back at the end. If you need another register, it's either going to be X or Y. Pick whichever one you want. I just happen to pick Y. So you're going to transfer that to the accumulator and push that on the stack because you need to save that register too. You can't mess these up. Now at the end here, we restore the values in the registers. So remember, we're pulling them off. So they're coming back in the reverse order they were pushed on. So we pull one off the stack. So that pulls the last value we pushed back into the accumulator, which was Y. We transfer that to Y. And then pull again, and that gets the original accumulator back. And then we do RTI. RTI is return from interrupt. Not to be confused with RTS, which is return from subroutine. These almost do the same thing, but RTI actually does a little bit more work. I'm not going to go into the details of this. You can look up some 6502 documentation. But if you mix up RTI and RTS, your program will probably blow up. So don't mess it up. So anytime you do a DLI, you're pretty much always going to be saving the accumulator, because if you're not using a register, what are you doing? You're not accomplishing anything. So the accumulator, you're always going to start by pushing the accumulator, and you finish by pulling it off and returning from interrupt. If you need more registers, you need to transfer them to the accumulator and save them as well, and then restore them at the end. Sometimes I need all three. Sometimes I don't. But you want to use as few as possible, because like I said, every single cycle counts in these interrupts. And this brings us to another issue, and that is that emulators don't always get these right. This is a very difficult thing to emulate because this is down to television frequencies and exact cycle timings. So whenever I start messing around with displayless interrupts, I always make sure I frequently go test on a real system, because emulators are pretty good, but they're not perfect, and you will run into problems eventually with displayless interrupts and timings on emulators. So always test this stuff on real hardware. I cannot stress that enough. When you start messing with displayless interrupts, you need to go test on real hardware from time to time, or else you're going to be in trouble. And I made this mistake with my very first 5200 game. It was called Ratcatcher. I went crazy with displayless interrupts, and I thought everything was cool. And then I went and tested on a real system, and it was a complete mess. So test early, test often when it comes to DLIs. Don't screw around with these. So to go back to the DLI here. So we're saving these two registers because we're going to change two colors. So we need two registers to put the color values into. So we start by loading one of them into the accumulator and the other into the Y register. Now this right here, sta WSync. So WSync is a special register. I believe it's on GTIA. Let me go check it. Go back to hardware.s. It's not on Antic, is it? Where is it? Oh, it is on Antic. Oh, I thought it was on GTIA. All right. So anyway, okay, so this is an Antic register. So when you write to this register, Antic will halt the 6502 processor until this current scan line has finished drawing, and then it'll wake it up. So this is how you time things. And it doesn't matter what you write there. You can write anything. So I just wrote whatever's in the accumulator. It doesn't matter. So if you don't do this, your changes, these color changes, will happen in the middle of a scan line. And you'll actually be able to see on the screen where these changes occur. Now, I'm not sure we would see it here, but just because of the colors we have picked out. And sometimes you can get away with it. And sometimes you need to, because you can't afford for the processor to be asleep during WSync sometimes, and you need the time. So you can organize things so you can actually get away with these changes without hitting WSync. But let's try this. Wait, let me finish talking about this, though. So after WSync, we're now in the horizontal blank area, which is where the beam has left the screen. So we can safely change things here without them appearing on the screen. So we write those two registers we loaded to the color registers. Now, these are not the same places we wrote up here. This is color play field 1, color play field 2. These registers are actually directly on GTIA. So we are, where are they? Here they are. These are directly on the GTIA chip. So we are changing the colors on the GTIA chip itself as it draws. These registers here that we have been using, these are called the shadow registers. These are actually page 0 locations. Now, part of the vertical blank interrupt in the BIOS, one of the roles it does is it takes all these colors from the shadow registers and writes them back into GTIA. So essentially, it restores the state of the colors to what it was at the beginning of the frame. That's why this top text line is still the correct color. Because we changed the colors after it. We never changed them back. Why would that be showing the right way? The reason it's showing the right way is because of these shadow registers. So think of the shadow registers as the colors you want to be set at the beginning of the screen draw. And when you change the colors in your DLIs, you don't write to the shadow registers, you write to the actual color registers on the GTIA chip to change those colors. There are some other shadows you might mess with, but generally that's how you're going to do it. And that's very important. Now, the way I structured this is kind of important here because you notice before the WSync, I loaded the registers. That's safe to do because you're not changing anything with the way the system's being drawn. So the usual pattern is you want to prepare your registers before the WSync, wait for the WSync, and then write them out because you don't have much time. You got to get that stuff out there. So you want to do as much work as you can before WSync. And then after WSync, do the important stuff. Do the stuff that's got to happen now. Now, we're going to be adding something else that happens after WSync, but it's not time sensitive, so we can do that later. But right now, we got to get this done. And that's why I use 2 registers here, because you usually don't have time to load a second value. I could have loaded one value, wrote it, loaded another value, wrote it to the second one. You don't have time for that. You got to have this stuff ready to go right now. And this also goes back to page 0 data. Now here I'm loading constants. Loading constants is relatively fast, but sometimes you need to load variables. You might need to load something from RAM in these things. And you always want to put data that your displayless interrupts are going to touch onto page 0 if you can, because those accesses are one cycle faster, and every cycle matters here. So I always like to make sure I've got enough page 0 data for any data that needs to be accessed by displayless interrupts. All right, but I've talked enough about this. Let's do a little experiment here. I'm going to comment out this WSync line. This might not show anything, but then again it might. Okay, it didn't show anything. Oh wait, no, I see it. Okay. Now you can see way over on the right side, there's a little gray line there. That is one of the color changes happening too early. Now, you notice the bottom text line is still all gray. So that is that gray right there being set too early. And it's actually showing up a little bit on that top mode line because I wasn't waiting for WSync. I just went and wrote it. So that change happened mid-scan line. So that's an example of what can happen if you don't wait for WSync. But I just wanted to show that. I wasn't sure that was going to show up or not. So, okay, so I think the interrupt actually fires then before the last line of mode 2 because sta WSync put me on the next line. So I think that's what happens there. Anyway, so we've got the first interrupt running. We have changed the colors from the text mode to the playfield mode successfully. Now, the second thing we need to do is we want to change the colors for that bottom text line. So for this, we're going to get another interrupt. And this one's, we're going to get this interrupt on the very last line of mode E. So this is going into that text line. So we're going to set this to 8, which means, again, displaylist interrupt right here. So the problem, though, is that when a displaylist interrupt happens, it jumps through that VDS list vector, wherever that is, right here. This is still pointing to this interrupt. So we need to point to a different interrupt. So let's write the second interrupt. It's going to look very much like, it's going to look almost exactly like this one. So I'm just going to copy and paste this one and make the relevant changes. Put a comment on it. Change back to text colors. And we need to give this an address so we actually know. So we'll give it, where was this? Okay. We'll do, oh, I don't know, 7020. Now, if this is, you always want to build at this point because that could be too close. It might be overlapping, and you'll get an error from the assembler if that's the case. But that's fine. We got space. So the second interrupt is a 7020. Now we're going to go back to the colors we started with, the ones that go into the shadow registers, because that's what we need for the text line at the bottom. And this is, again, this is playfield 1, playfield 2. So in the accumulator we'll put into playfield 1, that's going to be 0E, and playfield 2 is going to be 0. So we just need to change these to 0E and just 0. Okay, but we need this interrupt to run. So one thing you do is here in the first interrupt, after you've done the time-sensitive work, you change the address that the display list interrupt jumps to. And this is one of the reasons why you need to know the address. And you want to keep it on the same page, so that way you only change 1 byte. So now we need to change VDS list to hex 20. So that the next interrupt is going to go here. But now we've got the same problem again. Because the next time the screen draws, it's going to still be on this interrupt. We need to go back to the first one. So the way I like to, where I like to put this, the code that resets the interrupt, is in the vertical blank. Because this runs at the end of the screen being drawn, so it's the ideal place for it. Now, it turns out that the number we need to write to VDS list is 0. We already loaded 0, so we can reset the attract. So we can just put another store in here and write that there. So that'll reset the list, the interrupt, back to this one for the next screen draw. So now, if we did this right, both text areas should have visible text in them. It should be the correct color. And look at that. There it is. So to sum up again, we have 2 interrupts firing. One after that first text row, which changes the colors to the background, to what we want for the background. And then we have another one firing after the last row of the background, which changes the colors back to what the text row wants. So in this case, these colors in the shadow registers, which are restored by the vertical blank interrupt, they don't really do anything in this case because we happen to be going back to those very same colors at the end of the screen. But that's not always the case. So generally speaking, as I want to say again, the colors you put in the shadow registers, think of those as what you want the color to start at the top of the screen. Now let's do another little experiment because I want to demonstrate something that I actually did not know. And I learned this while I was doing Robin Banks. And it was very frustrating because it forced me to axe a feature I really wanted to do. Let's get rid of this W-sync in the second interrupt here. Now let's see what this does. Okay. I may have to look closely at this. Okay, that didn't work out like I expected. You can see at the very lower right corner is a little bit, it's like a little jagged where it turns black. Or again, I'm setting the stuff before W-sync, so it's actually visible on the screen. I expected that to be much more pronounced. Never mind. So the point I was trying and failing to illustrate was that, and you know, it might not show up in the way I think it would, but the amount of time you get in a vertical blank interrupt depends on the antic mode that you're interrupting from. Some antic modes are slower, and as a result, you get less time in your vertical blank interrupts. Now, the mode I used for Robin Banks happens to be one of the slowest antic modes there are. But it's also one of the most useful, so it kind of sucked. But I didn't have enough interrupt time to do one of the features I really wanted to do for that game. Whereas Mode E, I think, is one of the faster ones. So Mode E, I think, gets you a lot of time. And, I don't have a reliable resource for this. I don't know which modes, if there's a chart somewhere that spells all this out, maybe you could look it up somewhere. I don't know. Maybe there is. I should see if I can find one of those sometime. But it's not relevant right now. So we've got these two display list interrupts that change the colors mid-screen. How cool is that? You can change the colors mid-screen. Now I want to talk a little bit, just as kind of an aside, back to the 2600, because now I have never programmed for the 2600, and I have no desire to do so. But I know a lot about how it works, just on a theoretical level. And on the 2600, this is how you program it. You have to do a scanline by scanline guide, essentially, of the TIA chip as it draws each scanline and change the parameters as it goes down the screen. That's just how it works. Now, Antic on the 5200, you don't need to do it as often, but it's still something you need to know how to do, like we're doing right here, so we can get the colors right all the way down the screen. And there are some impressive things you can do with this. Like I said, the concept of sprite multiplexing, which, let me actually give you a visual example of that. So I'm going to go to Magical Fairy Force. If I can remember the command for this. Okay, great. So there's actually quite a lot going on here, but I'm not going to talk about this. I want to talk about the main game screen and not this screen. But once we get to pause here, okay. So wait for that lightning bolt to go away. Okay, so there's a ton of display list interrupt stuff going on this screen. There's colors changing all over the place. There's that collision detection harvesting I was talking about before. But the point I really want to point out here are the sprites. So the two player sprites are actually all four player objects stacked on top of each other. And somewhere in the middle, there's an interrupt that changes the position, the horizontal position of all four of those player objects, so that I can reuse them on the bottom half of the screen. So my man Porkchop up here in his yellow jumpsuit, he is all four player objects. So he has three colors. He's got like black, yellow, and the skin tone. And then one of the players is the wings in double wide mode. And then somewhere in this middle region here, which I keep pointing at the screen as if you can see that, but somewhere in this middle region, there's a display list interrupt which changes the position and the color of all four player objects to put them in the correct location for the player on the bottom. Although it doesn't change the wing color because the wing color is constant, but it changes the other three colors. And this is how I'm able to get these fairly detailed sprites, these three color sprites, as I'm reusing the player object. So you notice if you look at a lot of 5200 games that they tend to be organized vertically, in the sense that you have stuff on the top going down. As you go down, you move things around. And 2600 games are the same way. 2600 has even fewer sprites, and it multiplexes like crazy. Like this game is multiplexed just everywhere because I had to. That's just how it worked. In fact, if you look at the top of the screen here, there's some gauges. There's this gauge in the top left. That's two of the player objects overlaid on top of each other. There's those four red dots to the right of that. Those are the four missiles. And in the play field, those objects are all used again, like in the upper play field. And then in the bottom play field, they get reused from that character. And then the bottom of the screen, you see again, there's that gauge on the far right and the four red dots. That's the same thing again. The four red dots are the four missiles, and that gauge is two of the player objects. Actually, it might be three. Maybe even all four. I don't remember. It's the gauge is made of the player objects. I don't remember exactly how I did it now. But this is the sort of thing you can do with displayless interrupts. And it does get very complicated, and you have to put a lot of planning into it. And one thing you have to do is kind of lay out your screen sometimes to buy yourself time vertically. So this whole area in the middle here which has black. There's another example. I'm changing the background color in there at some point. So that's why that's black there. But that whole middle area, the players and the missiles aren't allowed. Well, the missiles are, but the players aren't allowed to go there. They're cut out of that area. So I can use that whole area in the middle to move the players around and recolor them. But that's enough of that. But that's an example of the sort of shenanigans you can get up to with display list interrupts. And any 5200 game of reasonable complexity is going to be doing a lot of that kind of stuff. Well, maybe not. I guess it depends on the game. Like, my last two games, IntelliDiscs and Robin Banks, actually use surprisingly little display list interrupt stuff. All right, so what have we just accomplished? We fixed the colors. We got the display list interrupt working. That's all good. So that is a very complicated topic. There's a lot to unpack there. And I recommend playing around with DLIs. Just play around with them, see what you can get away with. But I caution again, you have to check on real hardware. Because emulators don't get this right all the time. Very important. Must check on real hardware. But let's talk about what we're going to do next. Now, I do want to put some enemies on the screen, but I thought I might take a little bit of a delay and deal with something else. I wanted to talk about the rest of the stuff on the controller. Specifically the pause button. I thought we might write a pause loop, because that would be kind of a fun thing to do. So far we have read two things on the controller. We've read the joystick, and we've read the primary fire button here. Those are the easiest things to read on the controller, because you just go read them. Everything else on the controller has a catch to it. And I want to talk about some of that and actually do a little bit with the other stuff on the controller. So let's start by talking about this upper button right here and how that works. And I actually might need to refer back to some of my older code for this. But let's start actually by going back to the hardware file. Now here in the GT, I see we have trig 0, trig 1, trig 2, and trig 3. We've been reading trig 0. So the 5200 supports 4 controllers. So each of those 4 things, trig 0, 1, 2, and 3, those are the primary button for each of the 4 controllers. So trig 0 is the one for player 1's controller, trig 1 is the one for player 2's, and so on. The other buttons all work in a very, very different way. Now there is a register called console right here. This controls a bunch of things, but one of the things it controls, and what do we put in it here? We put 4 in it. Okay, that enables joystick scanning. One of the things this controls is which of the 4 controllers is currently being scanned for the rest of the input on the controller. So the joystick and the primary button are available from all 4 controllers at any time. The secondary button and all of the keypad buttons can only be accessed from one controller at a time. And you control which controller that is with the 2 least significant bits of console. So right now the value in the 2 lowest bits is 0, which points at the player 1 controller, which is the one we're using in the emulator. If you want to read player 2's controller, you change that to 1. You want to read player 2's, you change those lower 2 bits to 2, and so on. Now, this is one area where I'm a little fuzzy on how hard you can push this. I switch every frame at most, sometimes every 2 frames. I don't think you can just like switch it and then go read again. I think there has to be a frame in between. I'm not 100% sure, but I always do it that way. So if you're using more than one control simultaneously and you want to use those keys, you need to keep rotating between the controllers in console. I do it every frame or every 2 frames, it depends on the game, and switch them. But if you're using a game where you only use one controller at a time, like say Robin Banks, for example, has a 2-player mode where you use controllers 1 and 2. When controller 2 comes up, you just switch console to point at controller 2 and you're fine. But it's only when you're using multiple controllers at once that this becomes kind of an issue. So let's go ahead and try to read the secondary button. So we're going to go to where we currently read trig 0. Right here. And I'm going to change this code to try to read the other button. So let's see if we can do that. So go ahead and we're going to comment that out. So the way you read the other button is you load from a register called skstat. Skstat stands for serial keyboard status. Now this is a register that has something to do with the keyboard in the Atari 8-bits, but here it's a little bit different. So there is one bit in skstat that tells you the status of this upper button on the controller that's currently active, that you have selected via console. Now this bit is the shift key on the computers. So essentially the second button is masquerading as the shift key on the keyboard. And unfortunately, I cannot remember specifically what this bit is. So I'm going to go load up. I'm going to look at the code for another one of my games to get the bit here. So I want to get this right. Let's see. Well, it'll be in here somewhere. So this is IntelliDisk, which uses both buttons. So I'm just going to search for skstat. We're going to see what I do with it. Why am I not finding it? It should be here. Okay, that's weird. Oh, wait, did I break the input out or something? All right, we got to find skstat. Oh, keypads. Okay, I put it there. Okay. Well, this is good because there's a lot of stuff here. All right, skstat. So you see here, I load skstat and I look at bit 8 and I store it to keypad shift Y. Now I don't remember which bit, what the bit means. We'll have to test that. But we want bit 8. So with the trigger, if it's 0 it means it's down, if it's 1 it means it's up. I don't know which is which here. We'll assume it's interpreted the same way. So we'll leave the branch condition the same. So let's see what happens here. I gotta remember how I have the second key mapped on. I think it's shift on this keyboard. Oh, there it is. But you notice it's like, it's sticky. Yeah, like I'm pushing it, it's continuing to fire. I don't know if that's the emulator being dumb or what, but that's how you read that key. So most of the time with the keys, you want to have some sort of a debounce sort of thing where you remember the last state of the key and only do something if it's changed. I'm not sure why that's doing what it's doing there. I'll try running that again. But anyway, that one bit of skstat is what gets you the second key. I think the emulator is just delaying the read or something. So the emulator might be screwy here, but all right. So skstat bit number 8 tells you the state of the second fire button. So there you go. You learned something new. So that's how you read that button. That's relatively easy. The only real pain about it is that, like I said, you can only read from one controller at a time. So you need to set up a rotating queue of controllers that you read if you're going to do multiple controllers at once. If you're not doing multiple controllers at once, you just change console to point to whoever's currently playing, to their controller. Now the keypad is a whole different story. So the keypad includes these 12 keys plus start, pause, and reset. They're all part of the keypad. Keypad input is interrupt based, and it can get real ugly. So I'm going to refer to my old code here. In fact, I'm going to go back to my Robin Banks code because I think this is going to be a better example, because IntelliDisk had to do keypad for 4 players at once, so that code got kind of nuts. I'm going to just worry about one at a time, which Robin Banks does. Okay. So the keypad is interrupt driven. Whoops. I'm trying to open a file and screwing it up. Where did I define keypad cooldown? Might be in the game. I don't know. Where did I define that? Oh, it was in game. I just missed it somehow. Okay. Okay, so here we go. All right, so let's go ahead and set this up. So the keypad is, like I said, is interrupt driven. So there's some games you need to play to even get this thing working. And I'm going to go get some more coffee before we dig into this. So I will be back in a moment. Okay. So, the first thing we need to do is to set up an interrupt for this. Now, the keyboard interrupt works like the vertical blank interrupt did. So, just as a refresher, the vertical blank interrupt happens in two phases. First, you have the immediate vertical blank interrupt, which is this vector here, VV blank I, vector to vertical blank immediate. This is the first vertical blank interrupt that happens, and this is in the BIOS. It's a BIOS routine that does a bunch of bookkeeping and stuff, like restoring those shadow color registers. That's part of that interrupt. The very last thing that the vertical blank interrupt does is it calls through this vector, vector to vertical blank deferred. This is where you put your vertical blank interrupt. What you want to happen on vertical blank happens in vertical blank deferred. The keyboard interrupt happens the exact same way. See, here we have where is it? I'm just looking. Oh, here we go. V keyboard I, vector to keyboard immediate. So this is, again, a routine in the BIOS. There's a BIOS routine that does the initial handling of the keyboard interrupt, which is what happens when you press these keys on the controller. And just like the vertical blank, there is a deferred keyboard interrupt that at the moment is pointing to that end int, that interrupt end routine. But we're going to change that. We're going to point it to our routine. So I'm going to put it in here, even though I haven't written it yet. I'm going to call it keypad interrupt. Or keyboard. It's actually keyboard interrupt. We'll call it keypad, because this is 5200, not an Atari 800. Okay. So now we need to actually write the keypad interrupt. We're going to put it here with the vertical blank one. And we'll end the interrupt just like we do the vertical blank one by jumping to the interrupt end routine at end int. So first thing we want to do, as always, is make sure this thing is actually running. So we're going ahead and do the same trick we did before. We're going to increment the background color every time this happens, just to make sure. Did I typo that? I think I did. I did. Cat's yelling at me again. Why are you yelling at me? You want up? There you go. Okay, so we got a visitor here. Oh, she's leaving. All right, so I cannot type today. All right, it doesn't help that I can't see very well. Okay, so here we go. Keypad interrupt. So if we did this correctly, every time I press a key on the keypad, the background color will change. So let's see if we got it. We didn't. All right, so something's wrong. What's probably wrong is that we have failed to enable keypad scanning, is the most likely issue here. And I need to remember how to do that. This is one of those things I need to look up quite a bit because I do it and then I forget how to do it. Okay, so enable keyboard interrupts. Okay, so you have two different things you need to set. We need to set 40 to SIRQ enabled. Let's see if we did that. Wait, there's SIRQ enabled. No, we didn't. In fact, what did I... Oh, I did originally, but I messed it up by putting intervening code in there. The other thing we need to do is to write something to SK control, serial keyboard control. Looks like it's 2. So that's done. We did that. Okay. So hopefully now it'll work. Yeah, there's a lot of pieces you need to get the keypads working. And they still don't seem to be working. Shouldn't have closed that. All right, so what pieces am I possibly missing here? C0 to NMI enable, that might be what we're missing. No, there's that. All right, I'm not really sure what I'm missing here. I doubt it's this, so I'm going to throw it in there anyway. What could possibly be going wrong here? Maybe the background test isn't working for some reason. Let's try a different test here. Something else we could do. We're going to set HPause player 0 to 0, which will make it disappear from the screen. No, okay. Well, looks like we're coming across another issue here. And this happens. Like, Unfortunately, with these systems, there's so many weird little details you got to get right that you will very frequently run into problems like this where you have something you've done a million times and you can't figure out why it's not working. Like, why is this not happening? This happened to me on the first video where I screwed up something, and this is the same kind of deal where you say, well, why is this not working? Trying to check all the boxes here. There's so many little things you got to get. Yeah, I don't see it. I don't know what I'm doing wrong here. Doesn't help that the cat's screaming at me too. That's a shame. I really wanted to do this. I don't know why it's not working though. So what should be happening is that the keyboard interrupt in the BIOS figures out exactly which key was pressed. And it puts an identifier for that key into the accumulator when it calls your deferred interrupt. So you can immediately look at the accumulator and figure out what the key was. Now, the 1 through 9 keys on the keypad are the 0 through 9 keys are just that, 0, 1, 2, all the way through 9. So if it's a number, 0 through 9, that's the key that was pressed. The other keys have codes, which I have here in my, here. There's asterisk, octothorpe as I like to call it, start, pause, and reset. I was mostly interested in pause here. So we would compare for 0D to see if it was pause. But man, this is really bothering me. I don't know why it's not running that interrupt code. This is not the first time I've run into this sort of problem. Like I was just saying, no matter how many times you write these, you always, well, at least me, I always end up missing some little detail. And like, well, why is this not working? There isn't like a shadow register that's screwing this up, is there? You know, here I write to both the shadow register and the actual one. Let's try doing that. That doesn't seem right to me, but we'll try it. I mean, why not? It'd be funny if this actually fixes it for some reason. Oh, sure. Now it's working. Okay, well, there we go. All right, so we got the keypad working. Now, there is a problem here, though. I wonder if that shadow register doesn't do what I think it does. And I wonder if that does something different than all the other shadow registers. Now, there is one issue with this, and I want to point this out because this has burned me in the past, and it burns a lot of other people. This is another area where the emulator is not emulating this correctly. So here, when I press a keypad key and hold it, it stops. Like, it only does one interrupt. On a real 5200, when you press and hold a keypad key, it just keeps firing those interrupts over and over and over and over again. And this is one of the problems with the keypad input, and is one of the reasons why it's so awkward. There is no reliable way that I know of to tell that a key has been released. So what you need to do is you need to have a cooldown period. So after you actually get a piece of keypad input, you need to set a timer, and until that timer expires, you ignore all other keypad input. That's really the only way to keep from just getting spammed by these interrupts. Now, one thing you might notice if you pull up a 5200 game that uses the keypad keys on the title screen for some sort of option selection, if you press and hold the button, it'll keep going. There's a delay. Like, for example, Pac-Man. On Pac-Man's title screen, you can press one of these buttons, I can't remember which one, to cycle through the fruit to start in different stages. If you press a button and hold it, it'll like just keep cycling every couple seconds because there's a cooldown timer in there where it's like, do it, do it, do it. Because again, these interrupts, they just keep firing. So it's really difficult to do fast action with these keys, which was a problem I ran into with IntelliDiscs, where you use these keys like the Intellivision game to throw your disc around. And I'm going to sneeze. Excuse me. Okay, maybe not. So yeah, this is one area where this is getting it down. But that goes into the next thing I'm talking about, which is the need for a cooldown timer. So I'm going to go ahead and put the cooldown timer. I like to use the back end of page 2 for data that persists globally between states. So that's where I'm going to put the the cooldown timer. Keypad cooldown. We're going to put it at the very end of page 2. So it's going to be a 2FF. So here's what we're going to do then. In this keypad interrupt. Oh, wait, and then we need to do this. So this is another problem with the fact that the keypad is interrupt based. Since the keypad is interrupt based, you can't act on the keypad input right away because you have no idea what was happening when that key was pressed. You don't know where your code is. It's an interrupt. It could have been anywhere. So you really can't act on that information right away. What you need to do is to take that key press and store it somewhere and have a specific point in your game loop where you go look at that and say, okay, was a key pressed last frame? And then do something with it. So that's what we're going to do with these two variables here. We have last key pressed and we have keypad cooldown. Now it's also important to know that there wasn't a key pressed last frame. So I usually put FF, which is not a valid key code, into last key pressed. And I use that as a marker that tells me there was no key pressed last frame. So let's go back to the keypad interrupt. So as I mentioned, excuse me, one moment. That aborted sneeze turned into a little bit of a runny nose. So, as I mentioned before, the accumulator, when your interrupt is called, is going to contain the code for the key that was pressed. So what we're going to do is this. The very first thing that's happened in the keypad interrupt is we're going to look at the keypad cooldown timer. If that key is not 0, then we ignore the key. We say, nope, we're still in cooldown. Not going to take this key. And this will prevent the problem I mentioned before where you just keep getting spammed on the key. So at least you'll put a delay in there. So what we're going to do is we're going to load keypad cooldown. If it equals 0, then we're not in cooldown, so we can process the key. So we'll branch on equal. Well, actually, no, we'll branch on not equal. If it's not 0, then we're currently in cooldown. So we'll branch on not equal to done. Let's call it done, which will be right here before end int. So if we're at this point in the code, then we're not in cooldown. So we actually got a key press. So the first thing we want to do is start the cooldown. I generally use 15 frames as a cooldown. That's a quarter of a second. That's my usual cooldown length. You can come up with your own, whatever, experiment. But I'm going to load that and store it in a keypad cooldown. So we've now started. Oh, wait, no, I can't do that. Hold on. I just screwed up, actually. Remember what I said about the accumulator? The accumulator has the key code in it. So we need to use a different register for this. We'll use X. And then we're going to write the accumulator, which is the key code, to that last key pressed. And then we'll just flow through it and finish. All right, so to sum up again, every time a key is pressed or held, we look at the cooldown timer. If it doesn't equal 0, then we're in cooldown. We need to ignore this key press. So we branch down to done and jump to end interrupt. We're done. We're ignoring this key press. If we're not in cooldown, then we start the cooldown. We give it 15 frames, load it, write it, and we store the keypad code, which came in the accumulator, into last key pressed. Now, the main loop, well, actually, hold on. Let's finish the timer. So something needs to run this timer. So the best place to do this is game vblank, because this runs every frame. So if you want to break for 15 frames, this is where you want to put that code. Now, here we're not doing a whole lot, but in bigger games, sometimes your main game loop will not make it inside of an entire frame, and that's when you get slowdown. So if you have something you want to happen every frame, like a timer, game vblank's a better place to do it. So what we're going to do is we will load the keypad cooldown. If it equals 0, we don't care. There's no timer, so let's go to no cooldown. If it doesn't equal 0, we're going to decrement it. So there we go. Now we have the timer. The timer works now. So we need to do something with this information. And what we're going to do is we're going to implement pause. So a lot of people look at this controller. They see this pause key up here. And they say, oh, pause, cool. Some people think that happens for free. It doesn't. Pause is just another button. Internally, it's not pause. That's just how it's labeled. So if you want your game to be able to pause, you have to do it yourself. You got to come up with a pause loop. So here's what we're going to do. The first thing we're going to do every game loop is going to load last key pressed. Now remember, if last key pressed equals FF, there was no key pressed. Now, one way we can kind of shortcut this comparison here is by branching on minus, because FF is a negative number. No valid key code is a negative number. So what we're going to do is we're going to load the last key pressed. We'll branch on minus. If it's negative, then no key pressed. Nothing was pressed. So we just branch down to here. We don't care. Nothing happened. But if a key was pressed, we now need to figure out what key it was. So we're going to compare to one of those constants I defined. Key pause. Did I do that as all one word? I did. Okay. So key pause is 0D. That's the key. That's the code for pause. So I'm going to say, is this the pause key? If it's not the pause key, we're just going to go to no key press. We don't care about it. Well, actually, no. There is something else we need to do. Actually, let's do this. Let's do this slightly differently. Before I do this comparison, I'm going to load X with FF. And I'm going to write it to last key pressed. This is important because once you handle the key, you need to then allow a new key to come in. So if we discover a key was pressed, we're going to clear that, okay? Because we handled that key. So we got to clear the last key pressed by sending it back to FF. So the next key that comes in, we can tell a key was pressed again. Now, we still have the key in the accumulator, which is why I can overwrite this. And then we'll compare the accumulator to key pause. If it doesn't equal key pause, we'll just jump to no key press. We don't care. We're not dealing with any of the other keys. If it was key pause, we're going to jump to the pause loop, which I haven't written yet. So let's review this one more time. We look at the last key pressed. If it's negative, we jump to no key pressed. No key rest. Pressed. We jump to no key pressed because FF is our no key code, and that is a negative number. It's -1. And all the valid key codes are positive. So if that key code is negative, we know we have no key to act upon. There's nothing there waiting for us. If a key was pressed, we immediately reset that last key pressed code to FF so that we know we're able to handle another key in the future. Then we look at the key code that we got. Is it pause? If it's not, then we don't care. That's the only key we're handling is pause. If it is, then we're going to jump to the pause loop. So let's go write the pause loop. This will be the pause loop. So I mentioned, I think in the last video, that you will often have several game loops, several loops in your game, and the pause loop is one of them. So you want to follow the same pattern as your typical loop, which is you wait for vertical blank so you can sync up, do some stuff, and then jump back to the pause loop and do it all over again. So that's what we're going to do. But you notice what we're not doing is all this logic that we wrote up here. So the game's going to pause. Like everything's just going to stop because we're not doing any of this stuff. So what we're going to do in the pause loop is kind of the same thing we just did. We'll load last key pressed. If it's negative, we're just going to branch back to pause loop because there's no other work we need to do here. We're just interested in unpausing. Now, in a real pause loop, you might want to handle reset and start here. But for this little toy game, we're just going to deal with the pause key. If this were like a serious game I was going to release commercially or whatever, we deal with reset and pause here as well. But we're just going to deal with the pause key. So if it's negative, there's no key. We branch back to pause. Otherwise, again, we got to reset that key flag. So we reset it to FF. And then we compare it to key pause. So we can unpause. If it doesn't equal key pause, we branch back to pause loop. If it does equal key pause, we're unpausing now, so we jump back to game loop. In fact, this jump isn't even necessary. So that's our pause loop. And this should work. So let's try it out. So it's kind of difficult to tell if something's paused. The only thing we have that actually moves on its own right now is the missile. So I'm going to fire the missile and then try to pause it. Here we go. Fire, pause. Look at that. We paused. We implemented pause. Pause is a great feature. But you have to do the work yourself. Pause does not come for free. It's something you got to do. Now, if I press F3 again, it unpauses. There goes the missile. So that's how you implement a pause. Whoa. What happened there? Oh, never mind. I think I accidentally hit pause again. Yeah, so pause. Nothing happens. Unpause. There we go. So that was an interesting little aside. We got pause working. So what do we get here? We got those screen interrupts in to correct the coloring. I did briefly show how to use the second button, and we got the keypad input working, so we can pause the game. Now I think there's one last thing I'm going to do today, and that is I think I'm going to get some enemies on the screen. They're not going to do anything yet. They're not going to have any logic, but I'm just going to get them up there. So I want to get the other 3 players on the screen. I'm going to put them up there just to give us something to shoot at. So first, I guess we need a graphic for them, right? We need something for these players to look like. So we'll make up a new sprite here. For the moment, I'm going to make them all look the same. They'll probably have different colors, but we'll make them all look the same. So we'll do enemy sprite. Now I'm thinking of kind of a short, long sprite. I'm going to put it into double wide mode. So we're going to do a fairly short sprite. So we'll just do... let's see. How many pixels tall do we want this? We'll do 8 pixels tall. Then I'm going to pad it at the top. Whoop. Stupid thing. I'm going to pad it at the top with a row of zeros again, just in case we decide to do vertical motion on the enemies. But I'm not really sure. All right, so we're going to do like a simple kind of I was thinking about kind of like a spaceship, kind of a UFO thing. I don't know what this is going to look like. I imagine it's kind of like, whoops, what am I doing? Sometimes with Vim, you just hit keys and they do things and you don't know what you did. I'm going to do kind of let's do the first 4 pixels on the top will be filled in. We'll do that like 2 rows down. And then we'll have some empty space in the middle, I think. And then... Okay, I have no idea what this is going to look like, but this is going to be our little player sprite. Okay, so I'm going to write a function, a subroutine, that will draw the enemy. Now, what we're going to do, for right now, we're just going to draw it to a page. So we're going to use player objects 1, 2, and 3 for these enemies. So what we're going to do is we're going to draw the enemy to the address in how we want to do this. All right, we'll draw it to the page in FF at the coordinates in Y. And I think I'm actually going to do something interesting. It can be very useful sometimes to actually have your images be upside down, because sometimes it's easier to draw them from bottom to top. So I'm going to flip this around because it actually makes the drawing a little bit easier in this case for the way I want to do it. Okay, so it's upside down. I'm going to draw it upside down. Okay, so here's what we're going to do. So we're assuming the page we're going to write to is in FF. So we're going to just put... We're just going to put that there. Well, you know what? I could do it that way. Never mind. I'm doing this a different way. I'm going to put this back right side up. I'm not going to get fancy with this. That's stupid. All right, so how tall is this thing? 1, 2, All right, so it's 10. I'm going to do all 10 bytes just in case we do vertical motion later. So we're going to draw the player to the page in FF at the location in the Y register, or draw the enemy. So going to this routine, FF is going to have the page you're going to draw to. So player 0, the player we're currently using, is on page 14 hex. Because player missile base is 10 hex, and player 0 is at player missile base plus 4. And the player 1 is at plus 5, and then plus 6 and plus 7. So the page will already be in FF. That's going to be a prerequisite. And then Y is going to be the location on the page. So we're going to write Y to FE. So that's going to be the low byte. And then we're going to load X with there's a total of 10 rows. So offset of 9. Then we're going to do a loop. Okay. So here's what we're going to do. No, we're going to load Y with 9. Okay. Okay, so we're going to load enemy sprite indexed by Y. And we're going to write it to the address in FEFF indexed by Y. Decrement Y, and if it's not negative, loop again. And then return. Okay. So that should draw the sprite. So now we're going to go ahead and put the sprite in place for the other players. Now, I have not set a color yet for the other players. So there's player missile 0. I'm just going to grab some random color codes and shove them in there. I have no idea what this is going to look like. How about C5, PM1? We'll do, I don't know, 2-7 to PM2. We'll do F9. All right, I have no idea what these colors are going to be. And we also want to get them on the screen. So we're going to go ahead and put them at position, I don't know, 100. Yeah, so at the moment, I'm just trying to get these things on the screen. I don't really care where they go right now. So here's what we're going to do. So I'm going to draw the player 1 enemy. So he's going to go player 0, the player ship, is on page 14. The next player is on page 15. So I'm going to write that to FF. And we'll put it at vertical position. I'm just guessing here. I don't know what's going to work. We'll put some numbers in there and fix them later. Number 40. Why not? And then we'll jump to draw enemy. Now, I happen to know the enemy leaves FF alone, never changes it. So we can go to the next page just by incrementing FF. And this will be the next player. So we'll grab we'll move it down a little bit. He's 8 pixels, so we'll go down to 4A. And then go to the next player. Then we'll go down again to 50. I think it's too far, but I don't care. You know, no, I'll go a little farther. We get mess with details later. I just want to get these guys on the screen right now. All right, so let's see if this worked. Look, there they are. Okay, so there's the little enemy ships we made. Those don't look too bad. Boom. Now, I said I wanted to put them into wide mode. So right now they're a normal width. I want to put them into double width. So to do that, what we're going to do is we're going to load 1, and we're going to write this to size P1, size P2, and size P3. So this should put all of them into double width mode. And there they are. So these are double wide players. Now, they're still 8 pixels. They're just fatter pixels. There's also a quad width mode, which is twice as big as this, but they're still fat pixels. But you can see here, these are the other 3 player objects. Apologies, I've been a little sick lately. Lots of runny nose problems. So these are going to be our enemies, at least initially. So we're going to have to put some logic behind them to make them do something. And we have to make it so we can shoot them. So we need to do collision, which thankfully we're going to be able to use hardware collision for this. Hardware collision is fantastic when you can use it, but it's not always possible to use it. And of course, we're also going to want them to shoot at the player. And we're going to need to have the player die somehow. And we're probably going to want to do scoring. That's why I have this thing on the top, so you can do score. I don't know what we're going to do on the bottom. We'll figure something out. We'll use the bottom for something. Maybe we can have a shield or a health bar or something like that. We can put it on the bottom. So there's a lot of stuff we can do here. And I don't really know how much farther I'm going to take this game. I've illustrated most of the points at this, by now. But we're definitely going to go a little bit further with it. I think it might be just about done for today, I think. So I think next week, because I want to put some thought into what I'm going to do with the players and how I'm going to do with their logic. So I think by this time next week, I'll have figured out what I want to do with the enemies. So next week, we'll try to get them moving around somehow. And once we've got them moving around, we can start talking about collision. Now, what I'll probably do first is get it so the player can shoot them. That'll be step one. I just want to shoot the darn things. And then once the player is able to shoot them, we'll worry about them shooting the player back. And all the little stuff on the side, like scoring and new enemies popping up, right? Because we want more than 3 enemies. We blow them up. We want a new one to show up. So, there's all kinds of stuff we can do with this. We can come up with some new graphics, put different types of enemies. I may leave that as an exercise to the viewer. But, yes, this is all stuff we can do. But I think this has been a pretty successful day, aside from that minor hiccup where I couldn't get the keypad input working. But we've got some cool stuff going on here. We got the colors fixed up with the interrupts. We got pausing working. Pausing's good. And I expect we're going to do a lot more cool stuff next week. So I think for now, though, we're going to go ahead and shut her down. And within the next couple of days, I will post the code that we have so far to the currently running thread for this in the AtariAge.com forum. So if you're interested in the code for this project and want to goof around a little bit, just screw with it, go visit AtariAge.com, go to the Atari 5200 forums, and you can probably find the thread for this. And there will be a link to the code for this particular episode. And you can grab it, play around with it, and see what you can come up with. If you want to take this and run with it and turn it into an actual game at some point, hey, fine, do it. I'm happy to see that. But hopefully this will be helpful to anyone out there. And we've covered some very important topics today, particularly display list interrupts. And next week, we'll get back to it and try to get some enemy stuff going on and get these guys moving around. But for now, that's going to be a good night.